Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to try a little mental experiment with me.
Okay, I'm game.
Picture a clock, and not a digital display on your phone, but an old school, high-precision mechanical watch.
Right, like a really finely tuned gear system.
Exactly. You can hear it ticking, tick, tick, tick. It has a perfect rhythm, unshakable.
I am visualizing it. Reliable and steady.
Now, take that watch and throw it into the middle of a hurricane.
Well, that escalated quickly.
And not just a regular hurricane. Throw it into a jet engine that is somehow inside a hurricane. The noise is completely deafening.
Just absolute chaos.
The pressure is crushing. The turbulence is ripping literally everything apart.
And I assume my job in this experiment is to still hear the ticking.
Your job is to hear the ticking, but it is actually more than that. You need to measure the gap between the ticks to the nanosecond.
Oh, wow.
Because if that watch skips a beat, even by a fraction of a second, it tells you something about the wind and the pressure.
It tells you about the very fabric of the reality it is floating in. That is a terrifying level of precision. But I know exactly where you were going with this. You were talking about the galactic center.
I totally am. We were talking about a needle in the ultimate haystack today.
The biggest haystack we know of.
Right. We are looking at a discovery announced just days ago in February 2026. A team of astronomers using data meant to hunt for aliens has potentially found the holy grail of astrophysics.
The holy grail. It really is.
A cosmic clock spinning hundreds of times a second, hidden in the darkest, loudest, most dangerous neighborhood in the Milky Way.
Right next to the supermassive black hole, Sagittarius A star.
And Holy Grail is not hyperbole here. Scientists have been chasing this specific setup for decades.
Yeah, finding a pulsar orbiting a black hole is the dream. It is the one test of Einstein's general relativity that we just have not been able to run yet.
Exactly. If this thing is real, and we really need to stress early on that it is a candidate.
Right, it is not fully confirmed yet.
But if it is real, it is not just a new star. It is a laboratory. It is a way to break physics or prove it right once and for all.
It is a massive deal.
So today we are exploring a brand new paper. The title is On the Deepest Search for Galactic Center Pulsars.
Published in the Astrophysical Journal.
Exactly, on February 21, 2026. We are going to look at the machine they used to find it. We will look at the monster black hole it is orbiting.
And why this tiny, spinning, city-sized magnet might hold the key to understanding gravity itself.
It is a heavy topic today.
Literally the heaviest topic in the galaxy.
So let us start with the headline. This is fresh news, and it is a really interesting collaboration between Columbia University and Breakthrough Listen.
Yeah, the Breakthrough Listen part is fascinating.
Because when I hear Breakthrough Listen, I usually think of giant satellite dishes listening for little green men.
Right, the search for extraterrestrial intelligence.
Isn't that their whole mandate, looking for alien civilizations?
It is. That is their primary mission. They scan the skies for techno-signatures.
Meaning signals that look engineered by someone rather than just natural space noise?
Exactly. But here is the thing about hunting for aliens. To do it right, you need incredibly sensitive equipment.
Because space is big and signals are faint.
And you need to process a staggering amount of data. You are looking for narrow band signals in an ocean of cosmic static.
So essentially, they built a massive vacuum cleaner for radio waves.
That is a brilliant way to put it. A giant vacuum. And when you turn on a vacuum that powerful, you do not just suck up the specific dust bunny you were looking for.
You get everything else on the floor, too.
You get the background noise. You get interference from satellites.
Yeah.
And you get rare natural phenomena.
It is almost ironic. They were listening for a call from ET, and instead they picked up the heartbeat of a dead star.
Well, in astrophysics, one person's noise is another person's data. Breakthrough Listens has been surveying the galactic center for a while.
Why there, though? Why look for aliens in the middle of a hurricane?
Because, hypothetically, if you were an advanced civilization, that is a great place to put a beacon. It is the town square of the galaxy.
High visibility. Anyone looking inward would see it.
Exactly. So they're staring at the galactic center with the Green Bank telescope.
Which is this massive 100-meter dish in West Virginia, right?
Huge dish. And because of that, They are collecting some of the highest resolution radio data we have ever seen of that specific region.
So the research team basically saw this data sitting there and said, hey, while you are sifting through that hay, looking for alien needles, mind if we look for pulsar needles.
And they found one. Or, well, they think they found one.
They found an 8.19 millisecond pulsar candidate.
Yes, a candidate. That is a very careful scientific word.
It means do not pop the champagne quite yet, right?
Right. It means we see a signal. It looks like a duck. It quacks like a duck. But the pond is so foggy, we cannot quite see the feathers yet.
We will definitely get into why it is so hard to confirm later. I know the Galactic Center is a total mess.
That is a chaotic mess. But yes, they have a very strong signal repeating every 8.19 milliseconds.
Let us pause on the object itself for a second. An 8.19 millisecond pulsar. I feel like we toss the word pulsar around a lot in sci-fi movies.
We do. It sounds cool.
But let us ground this for you listening. We are not talking about a normal star like our sun.
No, not at all. A pulsar is what you get when a massive star dies. A star much bigger than our sun.
It runs out of fuel.
Right. It runs out of fuel and collapses under its own gravity. Then it explodes in a supernova.
The big boom.
The biggest boom. The outer layers get blasted off into space, but the core gets crushed.
Crushed how much exactly? Give me a sense of the scale here.
Imagine taking the mass of the sun, all that gas, all that fire, and compressing it into a ball the size of Manhattan.
A ball 12 miles across.
Roughly 12 miles across, yes.
That is just insanely dense.
It's inconceivable. A single teaspoon of this material would weigh 1 billion tons on Earth.
1 billion tons.
Yes. The atoms themselves are crushed so hard that the electrons and protons merge together to form neutrons.
Oh, so that is why we call it a neutron star.
Exactly. It is basically one giant atomic nucleus the size of a city.
Okay, so we have a city-sized zombie star corpse. But why does it pulse? Why is it acting like a clock?
Two things happen during that collapse. First, the magnetic field gets compressed, and it amplifies.
So it becomes super magnetic.
Trillions of times stronger than Earth's magnetic field. And second, conservation of angular momentum kicks in.
The figure skater effect.
Exactly. You know when a figure skater pulls their arms in and they suddenly spin way faster?
Yeah, they become a blur.
Well, imagine a star that was 1 million miles wide, suddenly shrinking to 10 miles wide.
Yeah.
It spins insanely fast.
And it has that crazy magnetic field.
Right. Because of the magnetic field, it beams out radio waves from its magnetic poles.
Like a lighthouse.
That is a perfect analogy. The beam is always on, but the star is spinning. So if Earth happens to be in the path of that sweeping beam, we see a flash.
Flash, flash.
Exactly. And that flash is the tick of our clock.
Okay, so for normal pulsars, that tick is fast, right? Maybe once a second?
Yes, a typical pulsar might spin once a second or so. But this object, this candidate, it is not a normal pulsar.
Because it is a millisecond pulsar, or MSP.
Yes, it is ticking every 8.19 milliseconds.
Do the math for me. How fast is that star spinning?
That is roughly 122 rotations every single second.
122 times a second. A city-sized ball of neutrons.
Yes, the surface velocity is a significant fraction of the speed of light. It is mind-boggling.
And here is the crucial part for our story today. Millisecond pulsars do not just spin fast. They spin with terrifying regularity.
They rival our best atomic clocks. They are some of the most stable timekeepers in the entire physical universe.
How regular are we talking?
A normal pulsar is like a cheap quartz watch. It might drift a little bit over a few years as it loses energy.
Yeah.
But an MSP will keep perfect time to within a microsecond over billions of years.
So nature essentially accidentally built a perfect chronometer.
Actually, accidentally might be the wrong word for an MSP. There is a whole backstory to these speed demons.
Oh, really? They do not just start out that fast?
Usually when a pulsar is born, it spins fast, but then it gradually slows down over time. It loses energy to the surrounding space.
So to get an old pulsar to spin 122 times a second.
It usually needs a partner. We call them recycled pulsars.
Recycled, like it gets a second life.
Exactly. The neutron star is in a binary orbit with another regular star. Its gravity is so intense it starts stripping gas off its neighbor.
It eats its companion star.
It siphons the gas off. And as that gas falls onto the neutron star, it spirals in and transfers its angular momentum.
Oh, so it physically spins up the dead star.
Yes. It is like hitting a spinning top with a leaf blower. You are adding energy back into the system.
That makes total sense. So finding an MSP usually implies a pretty complex history. A binary star system. Gas swapping.
Right. But finding one here, specifically in the Galactic Center, that is the real headline.
Which brings us to the location. because having a perfect clock is useful.
Very useful for astronomy.
But having a perfect clock sitting on the edge of a precipice is a whole different ballgame.
It transforms the discovery from a cool astronomical object into a fundamental physics test.
Let us talk about that neighborhood. The research describes this candidate as being close to Sagittarius A star.
SGR A star. The supermassive black hole at the absolute center of our Milky Way.
I feel like we often visualize the center of the galaxy as this glowing, beautiful, peaceful orb of light. But physically, what is it actually like there?
It is the most hostile environment you can imagine. It is a cosmic mosh pit.
Oh, mosh pit.
Yeah. In our neighborhood out here in the spiral arms, stars are pretty far apart. If the sun were a grapefruit in New York, the next nearest star is a grapefruit in California.
Lots of personal space.
Exactly. But in the galactic center, the stars are packed in tight. The radiation is just intense.
And there's debris everywhere, right?
Massive magnetic filaments, clouds of superhot gas, shock waves from old supernova explosions bouncing around.
And sitting right in the middle of this total chaos is the monster.
4 million solar masses of black hole. It dominates everything in its vicinity.
Its gravity anchors the entire galaxy.
And this pulsar candidate is apparently deep within its sphere of influence.
Now I have a question about that. If this place is so crowded, and if there are so many stars living and dying there, shouldn't the galactic center just be full of pulsars?
You would think so.
Why is finding one such a big deal?
That is actually known as the missing pulsar problem. It is one of the nagging mysteries of astrophysics right now.
Wait, there is an official missing pulsar problem?
A huge one. Based on the sheer number of massive stars we see dying in the center, there should be thousands of pulsars there, maybe tens of thousands.
But until recently.
We had found basically none.
Why? Are they hiding from us?
They are not hiding. They're being camouflaged. This goes back to our vacuum cleaner analogy from earlier.
Great listening for the radio click.
To find a pulsar, you have to hear those radio clicks sweeping past Earth. But the galactic center is filled with ionized plasma, hot charged gas.
And radio waves do not play nicely with plasma.
They absolutely hate it. It causes two massive problems for astronomers: dispersion and scattering.
Break those two down for me. Start with dispersion.
Dispersion means the high-frequency parts of the pulsar signal travel faster through the plasma than the low-frequency parts.
So the signal gets stretched out.
Exactly. The sharp click gets smeared out into a long slide whistle sound. We can correct for that mathematically if we are smart about it, though.
Okay, so dispersion is annoying but fixable. What about scattering?
Scattering is way worse. Imagine shining a crisp laser pointer through a pane of frosted glass.
The beam spreads out and gets all fuzzy.
Right. The sharp click of the pulsar gets blurred into a long, mushy hiss. And if the scattering is too strong, the pulse just disappears entirely into the background noise.
So the pulsars are there. They are screaming into the void, but the fog is just too thick for us to see the lighthouse beam.
That is exactly it. And that is why this specific discovery is so incredibly impressive. They did not just point a telescope and get lucky.
What did they do differently?
They used high-frequency observations, up around 4 to 8 gigahertz. Because high frequencies punch through that plasma fog much better than lower frequencies.
Ah, so they essentially changed the channel to a frequency that the fog does not block as much.
Right. But that comes with a major trade-off.
Yeah.
Pulsars are usually much dimmer at high frequencies.
Oh, so you were trading blurriness for faintness.
Exactly. It is a incredibly difficult balance to strike. Finding this 8.19 millisecond signal is a huge testament to the sensitivity of the Green Bank telescope.
And to the processing algorithms the team used to clean up the data.
Absolutely. The computing power required to sift through that is immense.
So we have a miracle detection of a perfect clock, sitting in a thick fog bank, orbiting a supermassive black hole.
And that proximity to the black hole is the key to everything, because when you have a clock next to a massive gravity, well, things get weird.
Einstein weird.
Very Einstein weird.
This is the part I have been waiting for. The Holy Grail. Why does Einstein's ghost care so much about this dead spinning star?
Okay, let us talk about general relativity. It is our absolute best working theory of gravity.
The core idea being that matter tells space how to curve.
And space tells matter how to move.
Yes, the classic bowling ball and the trampoline analogy.
Right. Sagittarius star is a very heavy bowling ball. It creates a deep, deep dent in the fabric of spacetime.
A 4 million solar mass dent.
Now, we have tested general relativity a lot here on Earth and throughout the solar system. and it works beautifully.
But those are weak gravity environments.
Earth is a tiny pebble compared to a supermassive black hole.
So we want to know, does the theory hold up in the strongest possible gravity?
Exactly. Does the math break down at the very edge of the abyss? That is what physicists are desperate to find out.
And the pulsar helps us do that. How exactly?
Because it is a clock. Imagine the pulsar is orbiting the black hole. As it goes behind the black hole, from our perspective, the radio waves have to travel past the black hole to get to Earth.
The ticks of the clock have to skim the edge of the crater.
Yes. And because space is severely curved, the path the light has to take is longer. It is not a straight line anymore. Space itself is warped.
So it has to travel further, which causes a delay.
It is called the Shapiro delay.
The Shapiro delay. So the tick should literally arrive late.
Yes. If we time the ticks, remember, they are incredibly precise. And we see them arriving slightly later than they should when the star is behind the black hole.
We can measure the delay?
We can measure the exact curvature of spacetime. We can map the pothole using a stopwatch.
That is incredible. You are using the delay of a tiny radio wave to map the invisible geometry of the universe.
And it gets even cooler than that. There's another relativistic effect called frame dragging, sometimes called the lens-Thirring effect.
Frame dragging? That sounds like a video game graphics glitch.
It is much trippier than a glitch.
Yeah.
Since the black hole is spinning, it literally drags space-time along with it as it turns.
Like a spoon twisting in a jar of honey.
Exactly. Space itself is twisting around the black hole.
So the pulsar is not just orbiting in a static dip on the trampoline. It is orbiting in a whirlpool of twisting space.
Yes. And that twisting should make the pulsar's orbit wobble in a very specific mathematical way.
And because it is a perfect clock, we can measure that wobble.
If we can track this 8.19 millisecond signal for a few years, we could potentially detect that precise wobble.
And if the wobble matches Einstein's math,
then he is right again. General relativity holds up in the extreme limit.
And what if it doesn't match?
Then someone wins a Nobel Prize because we have found a crack in general relativity. We would need new physics.
That is why we call this the Holy Grail. It is the ultimate stress test for physics.
There's no better laboratory in the universe for this than a pulsar near a supermassive black hole.
But, and there's always a but in astrophysics, we are not quite ready to hand out Nobel Prizes yet.
No, definitely not.
Which brings us to the uncertainty. We have to be very careful with our language here today. The research describes this as an intriguing millisecond pulsar candidate.
Candidate being the operative word.
Meaning they haven't officially hired it yet to do the physics tests?
Meaning they are reasonably confident they see something real, but has not been fully verified by independent observations.
Why is it so hard to confirm? I mean, if it is beeping every 8 milliseconds, can't another observatory just point their telescope at it tomorrow and say, yep, there it is?
Remember that crowded and turbulent environment we talked about?
The Times Square noise level.
Exactly. The galactic center is full of natural interference. There is dust, there's hot gas, there are countless other overlapping radio sources.
That is a loud room.
But the biggest enemy here is actually RFI, radio frequency interference.
Which comes from where?
Us. Yeah. Humans. We are incredibly noisy creatures in the radio spectrum.
Right. Satellites, cell phones.
Microwave ovens, airport radar, military communications. All of these things emit radio waves that telescopes can pick up.
So you were saying someone heating up a frozen burrito could accidentally mimic a pulsar?
It has literally happened before.
No way.
Yes. There was a famous case a few years ago where astronomers thought they found a bizarre new type of deep space radio signal. They called them peritons.
And what were they?
It turned out to be the microwave in the observatory break room. Someone was opening the door before the timer went off, and it let out a tiny burst of radio waves.
That is hilarious and tragic.
So astronomers are very paranoid about RFI. Now, the Green Bank Observatory is located in a national radio quiet zone.
Where they ban cell phones and Wi-Fi?
Yes, to prevent local interference. But satellites flying overhead, you cannot ban those. GPS satellites, Starlink, you name it.
So how does this team know their 8.19 millisecond tick isn't just a satellite passing by West Virginia?
They look for that dispersion we talked about earlier.
The slide whistle effect from the plasma fog?
Exactly. An artificial signal from Earth or a low-orbit satellite will not have that dispersion because it hasn't traveled through 25,000 light years of interstellar gunk.
It is clean.
Right. But this candidate signal does show signs of heavy dispersion, and the amount of dispersion is consistent with it being all the way at the galactic center.
Okay. That is a massive point in its favor.
It is a very strong piece of evidence. But they still need to reobserve it. They need to see it again, preferably with a different telescope or at a different time of year.
Just to ensure it is not a one-off fluke or some weird harmonic of local noise.
Exactly. Science requires reproducibility.
And that actually leads to a really unique and cool part of this story. Usually when a team finds a potential holy grail, they hoard their data right.
Oh, yeah. They lock it down until they can publish the final confirmation.
They say, this is my discovery, go get your own telescope.
Very common in competitive fields.
But this team is not doing that. The Breakthrough Listen folks are making the observational data publicly available.
It is a huge breath of fresh air.
Why are they doing that? Is it just pure scientific altruism?
Partly, yes.
Yeah.
It is a commitment to the philosophy of open science. But practically speaking, it is because the data is just overwhelming.
How much data are we talking about?
We are talking about petabytes of raw information.
Petabytes?
Yes. It is too much for one small team to comb through perfectly and quickly. By releasing it, they are essentially crowdsourcing the verification process.
They are saying, here's the giant haystack. Here is what we think is a needle. You all look too.
Exactly.
So theoretically, if you're listening to this right now and you happen to be a grad student in astrophysics or just a very smart programmer with a ton of spare computing power,
you could go download this data right now and help confirm it.
that is wild.
It is. The software they use to hunt for pulsars, things like Presto, which is a standard search code, that is open source too.
So the tools and the data are just out there.
You can run your own folding algorithms on the raw data. Maybe you find a totally different pulsar they missed, or maybe you find the final proof for this candidate.
I just love that. It is like a global public challenge. Here is a strange noise in the dark. Who wants to help figure out what made it?
It completely democratizes the discovery process. Instead of a handful of researchers holding the keys, the entire global scientific community can look at the ticking and weigh in.
And that widespread collaboration is going to be key. Because if this is confirmed, the payoff is immense.
Transformative, really.
Let us get into that payoff. What does success look like? We have touched on the general relativity aspect, the Shapiro delay and frame dragging.
Right, proving Einstein right or wrong.
But the researchers point out another major benefit. They note that confirming this pulsar could help us better understand our own galaxy as a whole.
Yeah, think about stellar demographics.
Demographics for stars, like a census.
Exactly. We do not actually know how many dead stars are floating around the center of the Milky Way.
Because the fog hides them all.
Right. Finding even one verified pulsar gives us a crucial data point. It tells us about the population density.
If we spot one, there must be others.
Statistics suggest if we found one under these incredibly difficult viewing conditions, there are probably hundreds or thousands more we just aren't seeing yet.
So it tells us about the history of star formation and death in the most extreme part of our galaxy.
It does. It also helps us understand something called dynamic friction near the black hole.
Which is what exactly?
How these dense star corpses slowly migrate inwards over millions of years, interacting with the black hole's gravity.
That is fascinating. And let us zoom out even further for a second. Astronomy is building some massive new tools right now, like the SKA.
The Square Kilometer Array, yes.
So how does this discovery tie into those future projects?
The SKA is going to be an absolute game changer for radio astronomy. It will be orders of magnitude more sensitive than the Green Bank telescope.
So finding this single candidate right now is almost like a scout finding a narrow path through the woods before the main army arrives.
That is exactly what it is. It proves that we can find pulsars in the galactic center if we look hard enough and use the right high-frequency techniques.
It acts as a proof of concept.
Right. It justifies the immense time and money needed for the next generation of searches. If we confirm this one candidate, it basically guarantees that when the SKA turns on, pointing it straight at the galactic center will be priority number one.
It is going to crack the missing pulsar problem wide open.
We might go from 0 pulsars to hundreds in a matter of years.
It really is amazing when you step back and connect all the dots of this story. We used the Green Bank telescope, which is this massive metal dish sitting in a quiet valley on Earth built by human hands,
to detect a tiny, spinning dead star acting as a perfect cosmic clock.
And nature just happened to place that clock right next to a 4 million solar mass black hole.
Oh, so we could test a mathematical theory that a guy with crazy hair wrote down on a piece of paper over 100 years ago.
It connects the unbelievably small and 8 millisecond rotation
To the unbelievably massive 4 million suns.
and it connects human curiosity to the fundamental fabric of the universe itself.
It really is a beautiful piece of science.
So for you listening, what does this all mean at the end of the day? Why should you care about a ticking star 25,000 light years away?
It means we are getting fundamentally closer to understanding gravity.
Gravity is one of those things we just take for granted. We experience it every single day.
It keeps our feet on the ground and our coffee in our cups. But physicists actually understand very little about how gravity truly works on extreme scales.
Or how it fits together with quantum mechanics, right?
Exactly. The grand unified theory. We know things fall down here on Earth.
But does gravity work the exact same way near a supermassive black hole as it does in your living room?
Einstein says yes. That is the equivalence principle. But we have to test it to be sure. This pulsar candidate gives us the chance to finally check his work in the most extreme laboratory imaginable.
So to wrap this exploration up, let us just quickly recap the key takeaways we have covered.
First, the discovery itself. An 8.19 millisecond pulsar candidate found near Sagittarius, a star by the team working with Breakthrough Listen.
Second, the massive potential. If confirmed, it becomes the ultimate tool for testing gravity, measuring the curvature of spacetime and detecting the twisting of space called frame dragging.
And third, the current status. It is unconfirmed, a candidate. But the raw data is entirely open to the public, inviting the whole world to help solve the mystery.
It really is the ultimate scientific cliffhanger. Is it a perfectly timed cosmic clock, or is it just complex noise?
That is the big question. We just have to wait and see.
You know, it makes me think about the nature of that ticking, assuming it is real.
How so?
That star. It has been spinning like that for eons. It has been ticking away in the absolute dark, 8 milliseconds at a time for millions of years.
Completely unheard by anyone.
Unheard. It was ticking like that when dinosaurs walked the earth. It was ticking when humans first discovered fire. It was ticking while we built cities and invented the radio and launched satellites.
Just sweeping its beam across the void over and over.
And it was only just now when we built a metal ear sensitive enough and an algorithm smart enough that we finally picked its tiny voice out of the chaos.
It really makes you wonder what else is ticking out there.
What else is hidden in the noise? The universe is incredibly loud, but if you listen closely enough, there is actual order in the chaos.
We just have to be patient enough to find the patterns.
Exactly. And here's a final thought for you to chew on today. The data is public. The confirmation hasn't happened yet.
Anyone can look at it.
Could the person who finally proves Einstein right or wrong be a student sitting in a dorm room right now just downloading that file out of curiosity?
It is entirely possible. The next Einstein might be the one looking at the data from the last Einstein's ultimate test.
Keep listening and keep looking up.
Thanks for having me.
That is it for today's show. Catch you on the next one.